Hi class. Today we're going to talk about session 5.3, Introduction to Logarithmic Functions, Math 110. Math 110. So logarithm base b function. So usually in here, if you see a logarithm function.
5.3 Introduction to Logarithmic.
Sorry. Okay. For the log function here, this is a form written as log b of x. In here, b is called base, right? So it is kind of the same as the base of an exponential function. And the x in here is like an argument inside of the log. Argument. Okay. Yeah. All right. So we call the log base b function undoes the exponential function bx. Okay. So if I have statement at b power a equal to c, which is equivalent to the statement that log base b of c equal to a. So it's a little bit like confusing for you, but you can try to remember as when you try to convert from log form to the exponential form, you can just take the base here, which is b, make it to power a, and equal to c. So we can call it b to a to power a equal to c. See that? So we're gonna have some more example later for you to see, but for now it's that, right? There is some properties of log, such as inverse probability. In here, I have log base b of x. I'm gonna repeat again. Log base b of b to power x will be equal to x only, right? So you see, if the base of the log equal to the base of the argument, so then that log will be the exponent of the argument, which is x. And in another way, for the inverse probability, you can also have like base b to power log base b of x. That also will be equal to x. So it look like the base of b can be canceled for the base of the log over on the power of base b here. So it's also can cancel each other. Common logarithm. So this is a very common one. If you take a look at your calculator, you can see they have like a log button. It's called log x or something like that, but it's never appear the base of the log. So it actually means as base 10. So if you have like logs base 10 of x, I can rewrite it as log x only. So there's like a hidden base 10 in here. Okay. Another one we call natural natural logarithm or natural log. Natural log is a logarithm with base e. Okay, e is an Euler number, like a constant number. So it and it can be written as ln x. So you can see here, like log base e of x can be rewrite as ln x. Okay, so ln means that is a log base e of x. Okay. One thing that you have to keep in mind that for the log function, you have to have x is always greater than 0. You have to have the argument is always greater than 0. So in here, I'm gonna write like argument always greater than 0. So in this case, I can say x is also greater than 0 to make it defined for this function. Okay. Let's move down. Uh-oh. Okay, so here it, oh my, 1 second. Right here. So I have one column talk about write the exponential equation for 4 square equal to 16 as an equivalent logarithm equation. So I would like to say, okay, in here base, what is that? Base is b. Base of the exponent is this guy, 4. So I'm gonna say 4, right? So so I'm gonna have logs base b, right, of x equal to c, right? So c in here will be the power, okay? C in here will be the power. So what is power in here? It is 2, all right? So I'm gonna rewrite, so I'm gonna have power C equal to 2, right? So I now can say log base b is 4. And the argument in here should be equal to 16, right? So is x. And that's going to give me 2, right? See that? So easily you can make an inverse for that. It's like 4 raised to 2 equal to 16. See that? So that needs to be the answer for this question. Right? So I'm gonna delete this and make a circle for this. Oh, okay. All right. Okay. So let's move down. Actually, before to move down, I would like to write as 4 square equal to 16 can be equivalent to log base 4 of 16 equal to 2. And another one is as like you have base b to power c, no, base b to power a equals c. Oh, why I have actually equal to c. We're gonna equivalent to log base b of c, right, equal to power a, right? So that also is a form for you to remember. So okay, all right. So now I want to emphasize that this a or this number 2 had to be the exponent. Okay. So now I will. I'm gonna say like, is this exponent of the exponential function? Okay. Now let's move down. To the definition of the log function. Okay, so log base b of a positive number x satisfy the following definition. Okay, so as I stated before, x or the argument have to be greater than 0. Also, base b as the same as the exponential function. Base b had to be greater than 0. Base b had to be not equal to 1. And so then y equal to log base b of x is equivalent to base b raised to y equal to x. Right, you can see that. Right. So, we read log base b of x as the logarithm with base b of x, or the log base b of x. Oh, same. What does it say? The logarithm y is exponent to which b must be raised to get x. So remember that this y is the exponent that b want to raise to get to x, right? Okay. So domain, as seen, the log and exponential function are inverse, right? The domain and range of the exponential function are interchanged for the logarithmic function. What does that mean? That means the domain of log gonna be the range of the exponential function. And the range of the log will be the domain of the exponential function, right? So so that we have domain of the log function with base b is always greater than 0. So similar with the range of the exponential function is always greater than 0, right? And the range of the log function with base b is all real number from negative infinity to positive infinity, similar with the domain of the exponential function. Okay, so let's move down. Here we go. We do problem number 2. Evaluate log of 1 million right? So this log mean that this is a log by 10, right? So so if I want to evaluate this one, I would love to use the property, the property 1 over here. Let me remind you. Okay. The property inverse, I mean the inverse property, right? I will try to make my base of block and the base of the argument will be the same. And then the log now becomes just the exponent. Okay, so let's go down. All right. So in this one, I would like to say, log of 1000 become 10 to power something. What is, because I have the hidden base 10 here, right? I mean, I can leave base 10 here, that's fine to me too, but you don't have to put it like, put the base 10. If you see a log, it's mean, without the base, it's mean base 10. Okay, now I want to have the argument change to be base 10. What is 10 raised to something to make equal to 1 million? I know that it will be 1, 2, 3, 4, 5, 6, 10 to the power 6, right? So I will know that from now, apply the inverse property. You can distribute the base 10 of the log and the base 10 of the argument, and now the answer should be the only exponent of the argument, which is number 6. Okay, so yeah. Okay, or if you write like this, logs by 10 of 1 million, right? You can think as means, right? 10 raised to what? To get 1 million, right? 10 raised to what? To get 10 millions. So you know that that's going to be the answer of the log. And you know that 10 raised to 6 to get 1 million, right? So this is like a method 1. And I would like to introduce another method, and this method like I usually do. I would like to say, if you want to evaluate log 1 million or anything, you just be equal to say equal to x, and you are looking for x, right? You will convert these to be exponential form. So you know that the base in here is 10. Now, in order to change it to be the equivalent exponential form, you just make 10 raised to x, right? And equal to 1 million. So I have 10 raised to x equal to 1 million. All right. And now I want to change the right hand side to become the same base with the left hand side. Okay, I have left hand side at 10 to the power x, and the right hand side become 10 to the power 6. Okay, so now you are having same base for both hand side. Then the power has to be the same. That means I have x equal to 6. Okay, and then that is the answer for this log 1 million. Okay, so so we can again say like log 1 million equal to 6 gonna be the answer, right? Okay, so that is for problem number 2, and yeah, you have 2 methods to do for this evaluate. I know that inverse poverty should be pretty easy for you to go with it quickly. But I mean, like the second method or the definition, it's called like the definition method, also work for you in some cases if you cannot make it to be same base easily. So you can do like me to see is easier. So let's go to the problem number 3 here and try to apply the to inverse poverty or method number 1 to determine each of these log. So I know that the first one have base v, base is 4, right? So I want to have the argument is base 4, right? So I know that logs base 4. Now 64, 64. If you take 64 divided by 4, you will get 6. And what else? Then sorry. You will get 12, right? Actually, sometimes I'm so stupid for this. No. It has to be 16, right? And 16 become 4 and 4. So that means what? This could be 4 to the power third, right? It's going to be 4 to the power third, right? Okay, now you can easily cancel the logs base 4 with the base 4 of the argument here, and the answer should be just the power or just the exponent of the argument, which is 3. Okay, I would like to use the other color for this. All right. Okay. So now let's come to the next one. So the log base 1 to 1 of 11. Oh, this one is not an easy one, right? You can see that. How can you make base 11 to become base 121? That's gonna be not an easy. I know that 11 times 11 will be 121. I know that, but how can you make from 11 to get to 121? Okay, if you think about 121 square root, what is that gonna be? 11, right? Or I can rewrite as 121 to power 1/2 gonna be equal to 11, right? So so now I want to change this number 11 to be 1 to 1 to the power 1/2. So that may be gonna be a good way to solve this problem, right? So I have 1 to 1 to the power 1/2, right? Okay. So so now apply the inverse inverse property. You can easily have that this is gonna be equal to the exponent of the argument, which is 1/2, right? This guy, right? Okay. Now let's move to the next problem. Okay. Log by 3 of 1. So this also can be like an special case, right? I'm gonna say any log, any base of logs. How do I say? Any log have argument is 1 will give you equal to 0. Why I can say that, right? If I think about, okay, I think about 3 raised to what equal to 1, right? Yeah, think like that. You can write by thinking, oh, 3 raised to 0 equal to 1. There is only one way to make is equal to 1. So then you had to make it equal to 0. So I can just say equal to 0. And I would like to have like a formula as log base b of 1 will always equal to 0. So that could be a special case for you to remember. And that also going to be the answer of this problem. All right. Okay. Another log in here, logs by 2 of 1 over 32. Okay. I'm trying to think like what 1 over 32 raised to what to get 2, right? So think about 1 over 32 to power something equal to 2, or maybe no. I gotta say 2 to power something equal to 132. Sorry. For that case, it could be look like, oh my goodness, is cannot make. I mean, you cannot make it easily, right? So, so think about convert this one to become like a negative power first. So I have 32 to power -1. That's going to be equal to 1 over 32, right? Okay, what else? I'm trying to make 32 change to become base 2. Because later on I can cancel the log base 2 by the inverse property, right? So 32, I know that 32 divided by 2 will be 16, right? And 16 will be divided by 2 going to be 8. And 8 divided by 2 going to be 4. And 4 divided by 2 going to be 2, right? So we have 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 number 2, which mean I can rewrite this at 32 rewrite as 2 to the power 5, right? So I'm gonna rewrite this at 2 to the power 5 and raise to -1 outside here. So when you combine everything, you can make it at 2 raised to negative 5, right? Because the power of power will combine by multiply the power, right? So you will have 2 to the power 5. And now you're going to change this log base 2 become log base 2 of 2 to the power negative 5 and equal to now it's become negative 5, right? So the answer has to be negative 5 because this is the exponent of the argument. Okay, so that should be problem number 3. Okay, so we done with section 5.3. I will continue with 5.4 in here. So 5.4 is graphs of logarithmic function. So let's do one example here. Consider the function fx equal to 2 to the raised to x and g of x equal to log base 2 of x. And then we're going to try to complete the table for both functions below. Then sketch the graph both function on the axis provided. So let's do in the left hand side here. I want to do for x and f of x equal to 2 raised to x. Right. Okay. So let's try to have some negative number first. Let's say negative 3. Then I have what? 2 raised to negative 3 will be 1 over 2 or third. Or 1 over 8. And then if I have negative 2, then I have 1 over 4, similarly, right? And then if I have negative 1, I have 1 over 2. Okay. And then keep going. So if I say 0, then it's become 2 to the power 0 going to be equal to 1, right? So this is going to be the y-intercept. And now I have like let's choose 1. I have 2. 2. I have 4. And 3. I have 8. Right. Okay. So for the right hand side, I would have another color. Okay, so let's do this at the x and g of x. Let's choose, remember that g of x is log. Now maybe I'm gonna have to move a little bit to the left. So here is x, g of x equals to log a2 of x. Okay, so let's say, remember that for this x you cannot make because x in here is a argument, and x for the log have to be greater than 0, right? This has to be x in here has to be greater than 0 for this log. Okay, so I have to say here's 1, or maybe I do 1/2 first. Let's see what happens. So I have logs base 2 of 1/2. 1/2 I can rewrite as 2 to the power -1. So that can become to -1 only. See that? I'm gonna try to make a nice number. I don't want to try to make something like something hard. Okay, so maybe I'm gonna choose something like 1/4 also. So what happened? Have logs with 2 to power 2 -2. See that? Remember that 2 to -2 is 1/4, right? So I'm gonna make it equal to -2, right? Okay. What about I have 1. You can right away know that logs base anything of 1 will be equal to 0, right? So that's we act intercept. Act intercept here. So look like opposite way of the inverse of the exponential function. Okay, so what else? Say 2. Have logs by 2 of 2, then it's equal to 1, right? Because this is 2 to the power 1. All right. So now I will try to have some point for the f of x first, using the red one, right? So first one was 1, 8, and -3. So -3 is here, and 1, 8 somewhere over here. What else? -2 and 1, 4. -2 and 1, 4. Keeps higher a little bit, all right? And then -1 and 1/2. -1 and 1/2, okay. And 0 and 1. Right here. What else? 1 and 2. 1, 2. 2 and 4. 2, 4. Okay. So look like we cannot do the last one. 3 and 8. So all right. So it will not go through x-axis. It just go along with it. So all right. So this is the exponential form. Fx equal to 2x. What about the log form? So 1/2 and -1. Here is 1/2. Here's -1. Okay. What else? 1/4 and -2. 1/4 here. -2 maybe somewhere here. Okay. And it will keep higher. Let's see, 1 and then 0. 1 and then 0. So it should be here. And then 2 and 1. 2 and 1. Uh-oh. Okay. 2 and 1. Right here. Not this. Okay. And I'm pretty sure it will go along with the y-axis and go to here. And if you want to see, you can notice that it look like this look like an flip to a line, go through the origin. Okay. So I will try to draw that line by the blue one. Okay. So the line that these two graph, the graph flip to is this line. You can see that? Like a mirror, right? See that? Okay. So that's for this problem, number one. Let's see what else we have. Problem B, how are the functions relate to each other? Okay, let me move out here. Okay. So you can see that, let me move a little bit up. You can see that from the graph or from the t-table, for the input, say input of, if the input of exponent, you will get, it will actually is the output of the log. So you see that input -2 here equal to -2 of the output of the log, and for the output of the exponential function is will be the input of the log function. So let me write down here that say input of log function is output of exponential function. In another word, it's going to be say output of log function is input of exponential function. Okay. I'm gonna say they are reflects. How can I say? I'm gonna say reflection of each other. Okay. Reflection. Each other. All right. And this is a word array. Okay. And lastly, say they are inverse. They are inverse. Okay. That's it. Okay. Now we're gonna find the domain and range, horizontal intercept and asymptote. Horizontal intercept is x-intercept actually. Okay. So firstly, say domain. You should know that the log function, the argument has to be greater than 0. In here, x is the argument. That means it's greater than the 0. Okay. What is the range? Okay, the range will be the same as the domain of exponential function, which is all real number. I say from negative infinity to positive infinity. Okay. So for the arc-intercept, in order to get the arc-intercept, you have to make g of x equals 0. So set g of x equals 0. Then I have log a2 of x equals 0. So then we try to find for x. So I have 2 raised to x and raised to 0 equal to x, right? So then I have equivalence exponential function as 2 to the power 0 equal to x, which mean x equal to 1. So then I have x-intercept in the order form gonna be 1, 0. For the asymptote will be y equals 0. I mean x equals 0 because why? In the exponential function, you have the horizontal asymptote. Now for the log function, it's going to be vertical asymptote because this is like invert of each other. So asymptote. I'm missing the p here, and double the s already. So okay, let me do that. Asymptote. Oh my god. Okay, vertical asymptote will be the y axis. We're going to be x equal to 0 on y axis. Okay, y axis function is x equals to 0. All right, that's it. So let's see the next page. Okay, next page is characteristic of the graph of fx with equal to log base b of x. Okay, so in order to do the characteristic for any real number x and constant b, with b is greater than 0 and b not equal to 1, right? We can see the following characteristic in the graph of fx equal to log base b of x. So firstly, it has to be one-to-one function. Okay? Secondly, it's y-intercept as 1, 0. Actually, this should be x-intercept. There's a typo here. Let me change it. X-intercept. So remember that this is x-intercept, not y-intercept. I can make it. Okay, give me 1 second. I fix this. I'm gonna delete this. Okay, and I'm gonna use black one. Say x-intercept. X-intercept at 1, 0. Oh my god. All right. So now x-intercept is 1, 0. And the key point is b comma 1. B in here is the base, okay? And you can see this is a key point. Okay. It will always go to this point, okay? And the domain is 0, infinity, from 0 to positive infinity. And the range will be from negative infinity to positive infinity. For x-intercept, I gotta say y-intercept here, right? Now, change this. Oh my goodness. So y-intercept, because the graph will never touch y-intercept. And this is y-axis, then there's none, no y-intercept. And the graph will be increasing if the base is greater than 1. Okay. See, so for the decreasing, it's going to be the base from 0 to 1, not including. Okay. So this is a graph for base b from 0 to 1. Okay, and it's go through point base b comma 1. Go through the x-intercept 1, 0. Okay, and it's decreasing, and you can see that. Similarly, you have the log function for base b greater than 1. That's the increasing, go through x-intercept at 1, 0 and go to the point b1. Okay, so let's move to the next page. Okay, I'm gonna stop this. I'll stop this video here, and I'm gonna see you next in the next one, next session at 5.5 later. Okay.